Welcome to Lecture 5 of the Signal Processing, this Introduction to Signal Processing course. There is a series of lectures I'm putting together on this, 32 in total, that will kind of go over an overview of the basic mathematical structures we need to consider in overall thinking about signal processing. In this lecture, we're going to focus in on the kind of systems we're going to start to consider broadly, and also properties of signals that we can leverage and exploit when we do our processing and mathematical algorithms to take these signals and use them for something meaningful in technologies. So we're going to start with this basic concept that we've already talked about, which is signal processing is about taking the signal, running it through some algorithms or some hardware, software to produce some kind of meaningful output Y. So we're transforming an original signal that might come directly out of a sensor into an output which we're going to use potentially for some kind of decision-making task in the system. Okay, so we'd like to understand the system that's here. We can have a continuous system, we can have a discrete system. So we want to think broadly about the system level processing. So when we draw this black box, it actually can be composed of many components. And in fact, it can draw from a vast host of different data streams into this system. So let's think about this from a mathematical point of view. X of t is going to go to y of t, or in a discrete, x of n is going to y of n. And what we'd literally like to understand is, what is the process that takes this original signal into this, this new version of the signal, this transform signal that we can use? Oftentimes what we try to do is create digital signals here, zeros and ones that we can transmit through long-haul communications or through our Wi-Fi or electronics, and then turn it back into meaningful signals, whether voice or vision, so that would be film or pictures in this. So you maybe start with an analog signal, turn it into digital signal processing, send it somewhere, process it, and then bring it back out into its original format for somebody else. So this is what we're thinking about, and we want to try to think of this out system levels and the kind of processes that can happen on the system level. So what kind of things can happen? Well, it's rarely just one thing you do to a signal. In fact, when you take an input, there are many things you may be doing to that signal. So you could process that signal in series. So this is a representation of it. So you take that input signal, you may do some processing originally, and from that process signal, you send it in to do more processing before you get an output. In fact, you can have many levels of serial processing before you get your desired output that you might use later in your system. You can also get things like parallel processing. From this input, your signal can go into two systems simultaneously where some processing is being done, and then these signals are recombined to produce an output for your system and technology. So, what this is sort of addition of signals. That's what this block diagram represents, and this is what this plus sign represents to the block diagram, which is an additive sum of these two signals. Of course, you can do fancier things with these signals, right? You can take these two signals and combine them in a diversity of ways, but this is, just the simplest representation of just beam or signal combining, single combination to come out with an output. Okay, so that's at the system level that you want to do. So we had serial processing, we have parallel processing here. You can also do series and parallel both, right? You can take your input, you can come through one pathway where there's a set of serial operations, system 1, system 2. You have another pathway with system 3, and then you combine these over here, maybe process some more before you get an output. So this is just a generic representation of a block diagram of all the kind of operations you want to do. So in other words, you're rarely just doing one operation to the signal. You can do an entire variety of operations. And so this here is trying to represent all the kind of operations you'd bring to the table. Interestingly enough, one of the things that we talked about in the very first lectures was what are the basic things you can do to signals. And, you know, for instance, time shifting of signals is one of the basic operations. And that becomes very necessary here because maybe there is some time it takes to process the signals, and maybe this is much faster. So when you combine them, you have to delay this signal so that all these get synced back up when you recombine here. Okay, so this idea of time shifting signals simply also comes as a consequence of the fact that as you process signals, if they are all running through these systems going through different signal processing operations, when I combine them, you'd like to combine them in a synchronous fashion before processing them further downstream. Okay, so that's going to be important for us to think about as well, as that's one of the basic operations we want to bring into play here. And this is also how you build technologies. You know, this diagram is sort of a simple representation of you know, what you have in a stereo system, what you have in your iPhone, what you have in a computer. It's levels upon levels of stacks of different components and systems doing signal processing before a desired output is achieved. So building technologies means that you have to do a lot of signal processing from inputs to outputs to get some desired results that are useful for yourself or for making automated decisions in various systems. Okay, so again, we just represent this by a black box, but this is just a transformation from input to output. And part of what we want to start thinking about is some of the properties we can exploit in our signals in order to do signal processing more efficiently. If we know certain properties exist in our systems, we'd like to know about it and take advantage of them. And so we can characterize signals in various ways. So I'm going to walk through a series of different definitions or properties that we want to be thinking about in our systems. One of them is memory. So memory in a system is really this idea that if you have a memoryless system, let's start with that first, that the future only depends on the current time. So whatever my state measurements are right now, that determines the future. So for instance, here's an example of this. My future is just or my output is just what my current end value is right here. And it can be some function that you give this thing, but that's the idea, is that there has no memory. It relies on nothing in the past. So you ask a question, does the system have memory or not? A system like this does not have memory, but a system as simple as this, y of n is equal to x of n minus 1, has memory. In other words, it relates to one time in the past. This is this n minus 1. Okay? So you start to see that memory systems are kind of interesting because the delay, so for instance, this is just a simple delay. This is what this function is. I delay this thing by 1 unit. That delay encodes a memory into your system. Here's another memory. It's the summation or accumulator. So your output is the sum over all the signals from the past to the current time. So this is interesting because this has the entire memory or entire history summed up into it, right? So very rarely you're going to sum all the way to the past. However, there are a lot of different systems where you are going to take a past of the system to inform some kind of output and some kind of decision. So this is an accumulator or a summer, summation. All right. So the summer is basically adding all these things up together. All right. Here it is, by the way, in continuous time. So basically the way I think of discrete time, anytime you see a sum, you know that when you go from discrete to continuous, it's going to turn into an integral, and this is the integral here. So you basically integrate the entire time history of your signal from the infinite past all the way to the current time t. And this is this here. And this shows that it has memory in the system, because whatever this y is, it depends upon the whole history of the system. But of course, it doesn't have to depend on the whole history. It can just depend on one time step in the past. Let's talk about invertible functions. So invertible functions are pretty simple. From a distinct input, I get a distinct output. So I can go back and forth with these. And so whatever my output is, there is one input only that can give that to me. That's kind of the idea. So here's some really simple functions, transforms. So I can take a transform y that is just 2x. So that is my function. And you ask the question, it's invertible. I want to find a way to get back to my original function. I can invert that by dividing by 2. So I take the output, divide by 2, I get a new function wt. And if wt is the same as x of t, then that means what I've done is I've inverted that function. And in fact, this is a very simple example, right? So this is a multiplication by 2. The inverse is division by 2. Okay, and so it's unique. So whatever I see in the output, I just divide by 2 and I get a unique output as well, or a unique inversion. So let me show you some invertible functions here. So x of n, I go through a system to get y of n, and then the inverse would give me w of n. And if w of n is equal to x of n, in other words, what I started with, then this is an inverter for the system. And if I can do this uniquely, then in fact, this is completely invertible, okay? Here, I just showed you this example. Again, x of t goes in here. Y of t is just twice the x of t, so that's y of t. And then wt, this inverter, is half y of t. So I get back to the original. Or you can even do something like this. X of n is the sum from the past to the present of the signal. And so this is like an integration step. The opposite of integration, differentiation. And so when you integrate this to get this y of n, the inverse of this is the difference. In other words, this is the derivative relationship, and that gives you that wn, which is in fact x of n. So this is really nice. So this thing here is an integrator that's a differentiator. They're inverses of each other. Okay? So ultimately what invertible means is whatever action I perform to that signal, I can just invert the process and get back the original signal. Okay? That's it. Let me talk about some non-invertibles. Y of t equals 0. So I take some signal, but y of t is just 0 on the output, no matter what x of t is. So there's no way for me, so this 0 is associated with all inputs. So there's no way for me to associate the 0 with a specific input. Another one, y of t equals x squared. So if I try to invert this, y is the square root of x. So plus or minus the square root. So there's two branches of solutions. So unlike this one, I can't say anything. This one here, there are two branches of solutions I could get back to. So it's not unique. So it's non-invertible. That's a non-invertible function. Okay. Let's talk about causality. So you see, we're kind of walking through all these important properties. We go from memory, invertibility. Causality is kind of just like what it sounds. Does the signal in the future depend basically on the past, the current and the past, right? If my signal, my output depends on the future, then that's not a causal relationship in a sense. So a signal only depends upon the current times in the past. So for instance, memoryless systems are causal. And the reason they're causal is because memoryless systems only depend on the current time. And so that's kind of the causal relationship that we have. Here's a non-causal relationship. Y of n is equal to x of n plus 1. So this is a point in the future right there. Okay? And so, or y of t is x of t plus 1. So this isn't causal in the sense that the past didn't produce this current state. This is something very different, which is the future produced this state that we're looking at, which is kind of a interesting concept in even of itself. Okay, so but you know, these are just generic representation of signals. All right, causality, and finally, one of the most crucial concepts we're going to consider throughout this course is this idea of the concept of stability. Now, you're actually pretty aware of the concept of stability in your everyday life interacting with physical systems. In fact, you know, you can think about something as simple as a pendulum. So here's the pendulum, and if you hang the pendulum from you know, here, here's your pivot point. You swing this pendulum, it swings back and forth, and it settles down right down here to this position here. And this position is stable because I can kick it, and then it swings right back down to this position. So we think about that as a stable point of the system. However, an upside down pendulum, so if I put it straight up, right, it's like balancing on a knife edge, smallest amount of perturbation will knock it over either to the left or to the right. So we think about it as an unstable system. And of course, if we're going to build technologies and we're going to build systems that are robust, in fact, we often use the term robust and stable. In other words, we want to be able to control it. We want to know that if the system gets knocked around, it still produces for us the state we need it to be in. Okay? So stability will be very important as we go forward, because we're going to think about, remember, these systems, they're embedded with lots of different architectures, and we're going to ask questions like, if I perturb that, do I still get a stable input to output relationship? And, for instance, in this pendulum you do, and this pendulum you don't. Okay? Mathematically, it's more like this. X of n, right, that's the input, goes to some output, and I just ask the question, does this output grow or decay, right? So if this thing starts to grow to infinity, then this system is unstable, okay? However, if the state of the system is a quiescent state, zero state, and this thing decays down to that, then I'd say it is stable itself, okay? So we will formalize these relationships. Stability is going to come down to thinking about mostly linear systems is what we're going to be looking at. And in linear systems, it's all going to be about calculating the eigenvalues of that linear system and making sure that we don't have any exponentially growing solutions in those, or exponentially growing solutions, which means eigenvalues that have a real part that are positive. All right, let's talk about time invariance. So this is an interesting concept, and it's about shifting the solution in time and getting back an output that is also has the same shift. So here's mathematically what this means. If I take a signal, x of n, and it maps to y of n, if I shift the input by n naught, and I look at the output, and the output is just y shifted by n naught, then I would say this is time invariant. Okay? So this property is really important. It tells you that you sort of have this behavior in the system that no matter how you shift time, you get the same underlying behavior to the system. And here it is in continuous time, time invariance. So I take this system here, x maps to y, and if I shift time and I get this y shifted by time, then I say this is time invariant. Okay? So that's a nice property of a system. There's a lot of systems we're going to look at that are in fact time invariant, including sines and cosines. So sines and cosines, remember, are going to be our basis for looking at a lot of signal processing. It's going to be a lot of Fourier transforms and Fourier modes. These are signal sines and cosines that persist for all of time, right? So you can go to infinity or minus infinity, and they are bounded between 1 and minus 1. All right, and here's the most important concept, linearity. Most of what we're going to study throughout the signal processing course is linear systems. And in fact, even if you get to very advanced systems, one of the goals is to try to approximate it by a linear system, because we can say a great deal about linear systems. Nonlinear systems are much more difficult. We can solve them. We can do simulations on the computer to do something with them, but with linearity, we can kind of guarantee performance. So part of what we want to do is start to understand some of the basic fundamentals of linear systems, which is going to be, in fact, the entire next chapter of lectures we're going to look at is linear time invariant systems, or LTI systems. The linearity has this very important property. Number one, superposition. If I have a mapping x1 to y1 and x2 to y2, if I add them, I get back out the mapping y1 plus y2. So in other words, I add them here, I can add them at the output. So this is linear superposition. Another way to say it, if I have a solution, I have another solution, I add those, there's still a solution. Another piece of linearity is that I can multiply my signal by any constant A, and it just multiplies my output by that same A. And by the way, A can be a complex number. Okay? We can combine this, superposition with this scale invariance, essentially, into one formula here. So for continuous time, here it is. I could take signal x1 and multiply by A, signal x2 and by B, and what I get out is the y1 times A plus y2 times B. That is from the continuous version, and then you get something very similar here in discrete time. Linearity, this is everything we're going to do in signal processing course right now is going to be hinging on this concept of linearity. Okay, all the mathematics is going to hold together because this is what we're going to use, is this idea that linearity holds. It's an absolutely critical property. And studying nonlinear systems, although they're very fun and produce very interesting behaviors, very rare we can say many things mathematically about them, but with linear systems we can say everything. And part of our goal is to engineer systems where linearity holds or approximately holds so that we can guarantee various behaviors and build robust and stable systems. Okay, so that finishes the set of lectures, which lays down some of the baseline for understanding some of the properties and some of the kind of ways of characterizing signals. And what's going to follow in subsequent lectures is we're going to start looking at these linear time invariant systems. And we're going to start looking at the properties of those kind of systems because we're going to be able to say quite a bit about those systems. And those are very well characterized with standard methods from differential equations and from eigenvalues and eigenvectors. And so that's what's coming up for us here in the signal processing world. So stay tuned for lecture 6 on that.